So I'd like to begin by thanking Sipide and Girish for inviting me to this. Just a quick intro, I'm a research fellow in the Department of Mathematics at Imperial College, the statistics section, and I'm also a group leader in the data-centric engineering program at the Alan Turing Institute. This talk is titled Bayesian Aerothermal Interpolation, if I could just summarize the talk in a single sentence, it would be the use of Gaussian process regression for inferring aerothermal quantities of interest. So this talk is really broken up into three subtopics. There's a high-level introduction to GPs, a quantitative, two case studies, the first of which is a quantitative Schlieren using GPs, and the second is estimating jet engine efficiency, once again using Gaussian processes. So at a very high level, I'm going to try to introduce Gaussian process regression, but perhaps motivated from the physical problem rather than from the underlying machinery. So consider a control volume as shown on the screen, and imagine for a second that we have a pressure measurement at a point within this control volume, this 2D control volume. You can also assume that because this is an actual physical measurement that we're taking of pressure, that owing to uncertainties in, say, static calibration, uncertainties in the data acquisition system, there is some uncertainty that's reflected in the pressure value we observe in this PSI value that you see on the screen. And that's characterized by this variance that you see in this PDF. Consider now another point within this control volume, so another pressure that we're measuring, and for different reasons, and some reasons of which are the same, we have an uncertainty in this pressure value as well. Now, our goal really is to understand how the pressure varies across this control volume, but we're just given two pressure measurements as denoted. Now, what we can do is we can assume that there exists some spatial relationship that seeks to draw a correlation between the pressure at any 2 points, including the ones we've just obtained the pressure for. We can further encode this relationship into a 2-point scalar value covariance function of the form as indicated on the screen. Now, there are various kernel functions we can use, quite a few of which are physics-based or physically motivated, but we'll stick with the standard squared exponential covariance function that has a form here. Typically, what tends to happen is that most of these covariance functions that we use that basically describe the relationship between any 2 points are parametric in nature. In other words, they're governed by certain hyperparameters. And so the two parameters that govern this squared exponential covariance, as you see on the screen, are a variance, which controls the alpha, and a length scale that controls the L in the denominator. So the idea really is that if we can hypothesize what kind of relationship there exists between the pressure at any 2 points in this control volume, we can move towards getting some sort of a prediction for how the pressure varies within this control volume. Now, in standard machine learning parlance, it's useful to introduce this idea of training data. So the training data in this context and throughout the context of this presentation will refer to the points where we actually get the measurements. Additionally, we have prediction points. So these are the points where we wish to determine what the pressure ought to be. And they're denoted here by various green circles. Hypothetically, at a very high level, what we're doing is we're assuming that both the training data, which is Gaussian in nature, as I said, these measurements can be assumed Gaussian, and the uncertainties arising from a range of different factors. We're also in tandem assuming that the pressure values that are going to be found at the prediction points are also Gaussian. So together we create this joint Gaussian distribution that really describes the pressure at any point within this control volume. And so this joint covariance that you see on the right-hand side is formed of a block of the matrix, the covariance matrix that's formed from the training data. You have a block that's governed by the prediction points, and then you have a covariance between the training points and the prediction points. So all of this will become a lot more clear as we march forward, but this just gives you a feel for some of the underpinning mathematics. For visualization purposes, it's quite handy to think of it in this context as well. So you have a block corresponding to the training, another block corresponding to the prediction points, and so on. Okay, so bearing in mind that our goal is really to estimate the pressure at the prediction points, we'd like to arrive at this conditional distribution. And this is basically stating what the probability of F asterisk, which is effectively the pressure at the prediction points, ought to be, given the fact that I'm observing the pressure along these training points as indicated before. And so this distribution, which we've assumed Gaussian, has a certain mean and has a certain covariance, and it's entirely defined by this mean and this covariance function. And so our pressure field is really given by these two moments as shown over here. Now, in a Bayesian context, what we typically assume is that these measurements are corrupted by a noise. So this basically informs what's called an observational model, or a likelihood that the probability of observing these measurements that I'm getting are given by the second formula on the screen. Then we have our model, which is driven by this covariance function as defined before. And the covariance function is underpinned by certain hyperparameters that it alluded to. So in this case, we have an alpha and an L. And typically these are inferred via Markov chain Monte Carlo. So this is kind of an overall relatively rushed overview of Bayesian inference in the context of Gaussian process regression models. Okay, so with this aside, I'm now going to delve into the two case studies that I mentioned. So the first question really is, how do we extract quantitative information from old Schlieren images? And this is a topic of research that collaborators and myself have been working on for more than a year now. And then in tandem, how do we calculate the efficiency of a jet engine? And while this may sound incredibly trivial, it's also incredibly challenging for a variety of reasons, some of which I hope to expose in the minutes ahead. So the first work really is with Bryn, who's a research associate at the Alan Turing Institute, and Andrew Duncan, who's a lecturer in statistics at Imperial College London. So all of you have undoubtedly heard of Schlieren images before, so I'll go through this relatively quickly. Effectively, a Schlieren image represents the refractive index gradient on a particular direction, and that direction is set by the orientation of a knife edge in a classical Schlieren image setup. Now, while there are a host of different quantitative approaches for extracting data, namely density estimates from a Schlieren image, all of them tend to require a very deep understanding and knowledge of the actual setup, so the way the image was taken. And what we're trying to do is really propose Gaussian process modeling as an alternative solution for quantitative Schlieren. So at a very fundamental level, you can think of a Schlieren image, and indeed any other grayscale image, as containing pixel values ranging from 0 to 255. And what we're trying to do really is come up with this transformation where we're going from Schlieren, which is effectively a quantity between 0 and 255, to what we call pseudo or scale density, and then finally to the density. And this two-way process where we're going from Schlieren to a density is going to be championed by Gaussian process regression. So recall the joint distribution I'd illustrated before. Now, if we simply take a linear operator or use a linear operator on this joint distribution, we also end up with a Gaussian process model. And in this case, what we're doing, that linear operator is simply taking the gradient along a particular direction, i.e. the derivative. And so we have this joint covariance matrix, as you see over here on the screen, and we also loosely define this squared exponential kernel, although you can use a few other kernels for this particular problem. So let me show you the step-by-step workflow. So you select a Schlieren image, you sample this image, and this basically gives you those Schlieren values. We use this Gaussian process model to inform a scale density, and provided with two density values, we're able to scale back to the actual density. And just for comparison, on the left, you see an estimate of the density from background-oriented Schlieren, and on the right-hand side, you see our prediction, bearing in mind that the only real source of data we're using are and is an old Schlieren image, and 2 values of density associated with the image. Since then, what we've done is we've also looked at inferring what those 2 values of density ought to be. And this can be done by using the isentropic relation. So if you have some notion of what the ambient temperature or Mach number is, you can work out what the density is at least 1 value. Okay, so in terms of ongoing work, one of the things we're really pushing forward is how we can use this on images when we have multiple Schlieren from the same setup, but with different knife edge orientations. And then also how we can leverage or work out what the density variation is using classical theta beta Mach number tables, where we're able to extract, for instance, the angle of deflection of a shock as it impinges upon a particular surface. Okay, with that, I'm going to now jump to my next question of interest, which is how do we calculate the efficiency of a jet engine? More specifically, how do we calculate the efficiency of a subsystem within a jet engine? And this is joint work with my colleagues. So accurate performance metrics, such as component efficiencies, such as pressure ratios in an engine, require accurate measurements. And while there's been a tremendous body of work dedicated to quantifying the uncertainties in fluid simulations, it's challenging really to deploy those paradigms that have been tailored for CFD directly onto experimental data. And the reason that is experiments are noisy, sparse, and possibly erroneous. And in a jet engine environment, there's this additional factor that there is, the flow is so complex that typical CFD setups aren't necessarily designed to emulate all the different frequency content you observe in an actual jet engine experiment. There are all these different modes that we don't necessarily know the origins of, and they exist only in the real engine environment. So just in terms of a quick state of the art, I'm going to actually focus on an isolated problem that relates to this idea of how we compute subsystem efficiencies, and that is the following. How do we exactly compute the area average, or indeed the mass average, of pressure or temperature? And the reason that's important is because if you think about efficiency for a second, efficiency is a function of average temperatures and pressures. And any rigorous estimate of efficiency has to be underpinned by a rigorous calculation of the true temperature or pressure over the annulus. So what we're going to do really is the following, is we're going to construct this Gaussian process model across the annulus, and we're going to be able to integrate this spatial field to be able to arrive at area and mass averages. So this is how we use the model in this context. Once again, we have training data, which here is designated by some rate measurements that we're getting from an actual engine. We derive this new kernel, so we're not using the standard squared exponential kernel anymore. We're deriving a new kernel that's physics driven. And what we're trying to do with this kernel is capture the circumferential variation in temperature, which is predominantly driven by some sort of harmonic forcing. And that harmonic forcing arises from the wakes and the upstream and sometimes downstream distribution of rotors and stators. And to do this, we're going to be using a Fourier series kernel. So I'm not going to go into too much detail. Suffice to say that depending on the application, your kernel can be physically, and indeed it should be physically motivated. So here's just a few snapshots of this model in action. So we have measurements, and then as I mentioned before, we're able to push these measurements through the model, and we're able to get an estimate of the spatial mean. And this is just a circumferential slice associated with the measurement. And more importantly, we're able to get an estimate of the uncertainty. Now, this uncertainty becomes particularly important because we can break down this uncertainty and really understand what's contributing to this uncertainty that we see along the annulus. As I mentioned before, one can take linear operators of Gaussian processes and also arrive at a Gaussian distribution. And so in this case, we take the area average of this Gaussian random field, and we end up with an actual temperature average. So this is actually the true area average temperature. And one of the things that this result, this derivation, while trivial, is so powerful, is because prior to this work, every time jet engine companies, and indeed within the turbomachinery community, when folks computed area averages, they primarily use what's called a sector weighted area average. So the idea is you work out how much percentage of sector area each sensor is actually taking up. And then based on that, you weight it. And then you use that to arrive at an area average. And now the problem with that as a metric is there's no guarantee of convergence, i.e. the more instrumentation you add, you have no guarantee that you're going to actually converge to a fixed value. Whereas with this one, we actually have some rigorous guarantees for convergence to the true area average. As I mentioned before I went on a deviation talking about the average, this uncertainty can be broken down. And this is effectively the law of total covariance in action. So you can break it down into an impact of measurement and precision, i.e. each sensor that I place in an engine to measure some quantity has a certain imprecision, and that's just by virtue of the sensor itself. And then there's also this notion of spatial or sampling uncertainty, i.e. I have too few instruments to actually sample my field well, therefore there's some uncertainty that arises from that. And just hypothetically, for this analytical example, if we only had one rake, you see the distinction between, or the distribution of the uncertainty across the impact of measurement and precision versus sampling. This is actually quite an important result because it actually tells engine manufacturers whether they need to stick in more sensors in an engine at a given plane, or whether they need to just increase the fidelity of the instrumentation, the quality of the instrumentation that's being used. Another really, I suppose, advantage of Gaussian process modeling is that it's fairly robust. And so in this case, even if you have missing measurements or anomalous measurements, you're able to quickly negotiate that, and you'll still get a spatial distribution for temperature and consequently its area average. Since we did this work, we're now extending this to multiple models. And one interesting opportunity for this is when one looks at testbed engines versus engines that are flying right now. So testbed engines are heavily instrumented, but they don't quite have, whereas their counterparts in the air have far fewer sensors. And so the idea is, how do you leverage the wealth of information that you're getting from a testbed engine and use that to better understand engines that are currently flying in the air? And so we're basically using a bit of transfer learning to really understand how we can exploit those measurements, because those measurements are, for a variety of reasons, slightly different. So with that, I thank you for your time. Apologies if it was a bit rushed, but yeah, that's it for me.